Let us first take the case of light damping and see what happens in this case. Remember, this case is where gamma square is much less than 4 omega 0 square, or gamma is much less than 2 omega 0. So, the amplitude in this case is f over m divided by square root of omega naught square minus omega square plus gamma square omega square. When frequency goes to 0, the amplitude goes to f over m omega naught square equals f over k. That means, at 0 frequency I am applying just a constant force and the mass is displaced. When frequency becomes large, the amplitude of the motion goes as f over m divided by, this is square, omega square, or f over m omega square. I have neglected this term in comparison with omega square. So, it is clear that if I were to plot the amplitude of the motion with respect to the applied frequency of the force, it will have a value f over k at omega equal to 0, and it will decay as f over m omega square far away. In between, this behavior for light damping is something like this, where the maximum occurs at omega equal to omega 0. If I increase gamma, it will be something like this. If I increase gamma further, it will be something like this. If you increase gamma, the maximum shifts slightly to the left, slightly to a value lower than omega 0, but for all practical purposes you can say that it is peaking at omega 0, and then far away it decays like this. So, if the driving frequency, if the frequency of the force that I am applying is equal to omega 0, the amplitude of oscillation becomes maximum, and this is again a reflection of phenomena of resonance. Recall that when there was no damping at frequency, driving frequency equal to the natural frequency, the amplitude was growing with time, it was not stopping. Here it becomes maximum, and this is again a phenomenon of resonance. We will see later that at resonance the power dissipated by the system, and therefore power given to the system is also maximum. What happens if I go to heavy damping? If you recollect the previous lecture, we recall that in heavy damping, without force, no applied force, the motion finally came to a stop like this. But in this case, no matter what the damping value is, the motion will always be there oscillatory, because x t solution in steady state is some amplitude cosine of omega t minus phi. However, when the damping is heavy, then if I were to plot the amplitude versus omega, it has no maximum, it starts with f over m and just decays. So, for low frequencies, the oscillator oscillates with large amplitude, always less than f over k, and then for larger frequencies the amplitude becomes less and less and less. This is sensible because for low frequencies force has enough time to act on the system and therefore displaces it. However, as the frequency of the applied force goes up, the system does not react, it does not have enough time to react to the applied force, and therefore its amplitude is very small. So, in general, if I combine the two, because light damping and heavy damping, if I were to plot the amplitude of oscillations with respect to frequency, the curve looks like this, this is light damping, and there is no maximum for heavy damping. The curve just goes like this. Nonetheless, the system does oscillate even in the case of heavy damping when subjected to an oscillating force. I can say that in this direction gamma is increasing. So, in light damping case, I do have a resonance at this point omega 0, which really reflects that the maximum, the amplitude becomes maximum at that point. How about the phase of the system? Recall that the system, when subjected to this force, lags behind the force by an angle tangent phi equals gamma omega over omega 0 minus omega 0 square minus omega square. So, for very low frequencies, if this is omega and I were to plot phi omega, for very low frequencies the phase is almost the same as the applied force. So, the system is moving with the applied force. Then at omega equal to omega 0, the phase lags behind, the system lags behind by minus pi by 2. At omega equal to omega 0, this becomes 0. So, tangent phi is infinity, and when the frequency becomes large, this is minus pi. The force and the displacement are out of phase by pi. So, when the force is maximum, the displacement is minimum. So, let us see how the displacement and force are in relation with each other at different frequencies. This is time x t. Let us say this is omega much less than omega 0. The force is like this, and in this case the displacement will also be following roughly the same graph. I have not shown the amplitude correctly, only the relative phases. On the other hand, if omega is much larger than omega 0, then if the force is like this, the displacement would be out of phase by pi. This is x t. Black one is f t. In between, therefore, the phase is somewhere in between, and so on. So, we have talked about the motion, steady state motion in the case of light damping and heavy damping, and seen how in light damping cases at omega equal to omega 0 the amplitude is maximum.